recording, so we're sure that nothing crashes, nothing goes wrong, and profiles work properly, so that we don't lose time, because it's very dense, and we know that it's very dense. And we have already seen some people feel a little bit lost or overwhelmed by all those new things. And yes, you basically learn a new engine in some way with the dot stack, but what you get for it is so powerful and so novel and new that it's definitely worthwhile to look into. So during the time while the video plays, don't be afraid to ask questions. We will try to answer them in the background, or we will select them to discuss live. Some of them are a little bit broader in terms of, like, mindset change, or do I need to lose everything I learned up to now to be able to use dots? And some of them are, of course, need to be a little bit more discussed. So continue to ask questions. We love those questions. We think many of them have a lot of relevance, and we will try our best to answer them. And also, no one currently is an expert in dots, except maybe with the Unity team themselves, because it's so new and data-oriented programming has not existed for that long. And Burst is new, everything is new. So it's the perfect time to ask questions and be worrisome about certain things, because that's the perfect time where we will learn what is still needed, what we can improve, and how we can best teach those concepts that you're completely good with it. So let's jump into the videos. And there's also a poll that's mainly for us to know, like, where you stand. Have you already worked with dots, or even with ECS? Have you already maybe shipped a product which uses dots? It would be very interesting for us to know where you currently stand, that we also know the audience a little bit and tone things down or up for the next iteration where we talk about dots again.
Perfect. So yeah, we are running the hands-on part right now. Please continue the discussion on chat, but don't submit your questions on the chat. It is very difficult for us to find. So we will also run a few polls just to understand the expectations from this workshop, from dots, and the level of the audience, so we can share more details according to the audience. So yeah.
Welcome to Unleashing the Power of Dots. We will walk you through a small and a little bit contrived example of how you can use the production-ready parts of the dot stack to enhance your current applications, even though they're built fully in monobehavior land. So a little bit about the speakers today, or who helped prepare this presentation. First, we have Dreaming I'm Latios. If you have ever been on the Unity forums since basically ECS or dots existed, and you had any questions, chances are that you got a very friendly and helpful answer from this person. He has been very helpful within the whole community and has given advice on the most complicated problems we had, and also even created his own framework called the Latios framework, which is built on top of the dot stack. So if you ever build an ECS-focused application in Unity, I would heavily recommend that you at least check out this framework. He gives solutions to many things which often crop up on the forums, which people have problems with, like shared containers, as well as singletons and all of the other things which have been solved in a very interesting way. And also, if you want to see very advanced dots implementations, please check out this framework. There's a lot of example codes which are very helpful. About myself, I have started more as an economist, then moved to being a bioengineer, and then finally became a computer scientist, and then worked in a few companies, and now started together with Dennis Conrad Holonotic, where we are basically exploring the cutting-edge technologies in spatial computing as well as inside Unity to try to squeeze out the most interesting things possible in the current domain. Well, enough about how that all got created. Now about the challenge. So we have a certain task to do. So one thing happened. Your boss actually fell in love just a few days ago, and he really has his brain chemistry completely altered to that, and now he wants to spread that information to everyone in the world. And of course, he wants to use the currently published experience to have hearts everywhere that he can showcase his love to everyone. Evidently, we have to have a certain frame rate to be targeted that the users can still play it, although that hard promotion is actually running. And the main thing is do it fast, don't ask too many questions, and just get it done, basically. So you go back to your desk and you think, okay, you know that that hard promotion will probably not last very long. It's very likely that brain chemistry will go back to normal, and we all realize that that hard promotion was not the best thing. So we don't want to spend too many days on figuring out a good strategy to make it happen, although we want to please our superiors that they think it's perfectly implemented. So our first strategy is just to spawn little hearts, make them pulsate and animate in the level, and we spawn as many as we can that it feels like the whole level is filled with hearts. And in the first implementation, we do not care about frame rates. We just care about getting the right number of hearts that it feels that it works well. We also don't try to do it very sophisticated. We really do the simplest way possible. Here in Unity, we can see we have used the 3D game kit, which probably most of you have already played around with, to have a complete game. And to that complete implementation, we added the hearts promotion as an additional feature. And if I press play here, you will see it's the second level of the 3D game kit, and there's basically nothing else in there currently, and we also added a little bit of a FPS counter on the side that we can see how many frames we have. So as we see here in the normal game, we have exactly 60 frames per second, on average it's 60 frames per second, so that is a perfectly playable experience. And now we start to add the hearts promotion to add that additional features which we got requested to add in a very short amount of time. To add that, we added a hearts manager, and as you can see here, it's just a mono behavior with an additional component. It's called the heart promo manager. What we have here, we just have the hearts prefab, we have a spawn zone to indicate where the hearts will be spawned, and we have a list of all the heart objects. We also have a total number of hearts variable, which we can adjust in the editor to just move those hearts up and down. In addition, there is some boilerplate code, but the main interesting part is we just, on awake, we instantiate and spawn the number of hearts which we defined in the editor in a random location of that spawning volume, and then each heart has its separate logic on it to actually rotate, which we can see here in the hearts promo logic. Each of those just oscillate a little bit and bump a little bit up and down and rotate, and that's basically the animation we added to the hearts. So once we have this, we can go into Unity and we set it in the beginning just to 1,000 hearts, and the red volume you can see here is just the spawning volume which we spawn all those hearts, and we try to make it big enough that it encompasses basically the whole level. So let's quickly press play. Okay, let's have a look on how it is if we spawn in the full level 1,000 hearts. As we can see here, we don't see any of them. It looks like actually that the 1,000 hearts we spawned never got created. Oh yes, here we see a small little heart currently being displayed, but it definitely doesn't look like there are many hearts in that level. It's just one tiny one there. Now the question is, of course, might it be that we actually didn't spawn the 1,000? We have some kind of error in the logic, but as you can see here, a lot of those are definitely there. The main problem is just that there 1,000 hearts in that size of a level is just not enough. So of course, the next step is we have to find out which number of hearts do we actually need to get to something acceptable. And you do it with an increment of a 1 power of magnitude. So instead of 1,000, we spawn now 10,000, and we will have another look and see if that will be enough to have convincing heart promotion going on. So let's have a look around. Now we can see it's more easier to spot a few hearts, right? There are a few, but it still doesn't feel like there's a lot of love going on in this level. So let's bump it up by another order of magnitude, and let's see what happens when we spawn 100,000 hearts in that level. And of course, we don't worry about performance at this stage. We just say, okay, how many hearts would be needed with the most simple logic that we just spawned all over the place. And we can see, like, with 100,000 hearts, it looks like, yeah, that's about the number which feels like, okay, there's a lot of hearts being around, and it feels more or less good. Of course, the frame rate is probably not anywhere in the level of acceptable, but at least we have determined that with 100,000 hearts, we can actually launch that promotion, and it will feel good enough. Now, when we go back here, and we get to the results of that first iteration, we have a slight problem. So the hearts are there, we're really happy, but the 3 frames a second from the initial 60 is actually very terrible. And we found the required number of hearts, but we also see that when we look into the profiler, we see that hearts promotion logic, like the update method, which spawns those hearts, and then each of those 1,000 instances of the hearts, they take together 83 milliseconds, which is definitely nowhere to be acceptable. But so we cannot have 100,000 game objects in the world and expect the hearts promotion to be playable in any feasible manner. Now, for the second iteration. As we saw before, 100,000 hearts as game objects being displayed at the same time without any additional logic is just not feasible. So we go for a different strategy. We know that 100,000 hearts are necessary to make it feel like there's really a hearts promotion going on. But those hearts don't need to be presented as game objects all the time because we cannot see most of them. So we go for a pooling strategy, and we only represent virtual hearts, the 100,000, and then from those 100,000 virtual hearts, which are randomly distributed, we will focus on the 1,000 which are closest to the camera and inside the view frustum, that we can basically use a pooling technique. As soon as we move the camera around, we basically only display the 1,000 hearts of the 100,000 which are currently closest and inside the view frustum. That should give us a better performance because we don't have 100,000 game objects all at the same time being animated and consuming logic. We only have 1,000, but the player should barely notice the difference because he will only see the ones which are close to him. The ones behind him, as well as those far away, will actually not be visible. So let's go into code and see how that was implemented. Again, do not focus too much on the implementation part of this, as that is not the important part. The more important part is it's about the strategy of how can you get to better performance while using data abstractions and virtualization of things. So for example, here we have the heart data, which is implemented as comparable, and it has a position, a distance to the camera, an index, which we'll use to define which is currently visible, and it has a boolean to know if that heart is currently actually visible or not based on the view frustum. And then we also have a compare method, which allows us afterwards to sort all those 100,000 hearts which we create by giving the ones which are currently visible priority. So if the one is currently visible compared to another heart, then that one has priority. And if both of them are visible, basically if the result is 0, then we prioritize the one which is currently closer to the camera. This is basically a custom sort function based on our requirements of which hearts we want to be sorted first when we sort an array of those virtual hearts. And the rest is very similar. We have just camera planes, etc. We instantiate the hearts exactly as before. We have a heart pool count now of a limited number of hearts instead of the 100. In the update method, we basically go through all the hearts which we have, and we check them, the bounds of them. For that, we use the Unity's implemented geometry utility to test which one are in the view frustum of the camera, and we also calculate the distance from the camera the hearts are, and then from that, we can use our custom sorting function to get the first 1,000 hearts which are the most closest and inside the view frustum, and we then do some swapping logic. You don't need to worry about that here. we just swap the hearts that those which are currently visible and the close to the camera are in front of the array, and those are the ones where the pool then gets the position set to, and so we can have then only 1000 hearts and prioritize the ones which are currently visible. And if you go back to Unity and press play, we can see we still have the impression like there are 100,000 hearts because they're visible all over the level, and we currently have around 15 to maybe maximum 20 frames a second, and that's not really there yet. It's already much better than what we had before, but it's not really playable yet. And the good part is that we only have 1000 hearts as game objects actually represented, but it still looks like that we have a real hearts promotion going on in the game. And now when we look at the profiler from the currently running process, we can see that the hearts pro manager, this logic, the update logic where we sort and handle all the hearts, is actually the one which takes up the most time. It takes up nearly 50 milliseconds. And so we have to find a way, although we are on the right path, as we can see, we definitely have better performance than before. We still need to find a way to update that sorting and prioritizing logic in a good way that we get to an acceptable frame rate. And if we summarize, what happened before is basically we reach around 15 to maybe 20 frames per second. We still know that the bottleneck is the update function, and sorting step is very expensive. We also have many threads which are sitting idle. When we go back to the profile, we can see that here in the job, we can see that nearly all of those threads, the worker threads from 1 to 14 in this particular machine are just sitting idle and don't do anything while the main thread is extremely busy. So of course there, if you can do some kind of parallelization and improvements, then probably it could help us to get to a higher frame rate. And also we see that the main bottleneck here is the hearts.update function, and we will look in the next iteration how to improve that. Version 3, in the third iteration, we try a different strategy to get a little bit better at what we did before. So we have noticed that we have a few threads which are just sitting there not doing anything. So it would be probably a smart idea to start to put some of the work which are currently done on the main thread on those worker threads, so the main thread can do something else. So to do that, we use one feature of the dot stack, which is the jobs. The jobs allow you to schedule certain tasks to be done not just on the main thread, but actually to be done on worker threads, and even further down the line on multiple worker threads at the same time. But we will come to that. But to use the jobs, there's certain restrictions which apply. So what type of jobs you can execute need to have certain data types, and certain functions are not yet fully available. So for example, we need to implement our custom sort function because the array.sort, for example, is not really available in the dots job stack that you can directly use that. It has a few restrictions. I don't go into detail now, but just be aware that we had to implement our custom sort function as well as a custom thrust and check function, because the one which came from the geometry utilities could not be directly run inside the jobs. And when we go directly to the code, because the actual in the implementation nothing changed, it's more like in code where we see a lot of things change. So we have the hearts pool job which implements the iJob interface, and the only method which you need to implement is the execute method. It just means that here you will do the work and you have to pass in all the data points which that execute method will operate on. Again, if you are new to the dot stack and it's a little bit overwhelming, don't worry about it. Just focus on the high level picture of the strategy. We can run certain things on worker threads instead of the main thread by implementing that iJob interface. Here we just go through all the pool records, which is a new data type we added. It's just an optimization strategy where we have the position of the heart and then decide if we should write that heart to this frame, so if we need to update the position of this heart to this frame, or if it was already visible in the last frame. That's just a little optimization that we don't need to update the position of hearts which were already visible during the last iteration. And we go here through all the hearts. We do a similar strategy as we had before. We calculate the distance to the camera. Here we actually approximate it with the distance square because it's good enough for our implementation and it is faster than calculating the actual distance. And then we have a custom test planes function which allows us to check if something is inside the view frustum. We use the dots product. It's just an approximation, but it's good enough working in this example. And then we have our custom sort function for the hearts array, where we go through and basically and sort all those hearts to be the first 1000 to be there when they are inside the view frustum and close to the camera. And then we go through all the hearts and swap again the hearts around and adjust the position of those actual game object hearts to be the ones of the 1000 closest to the camera and inside the view frustum. For the test planes one, we just use a dot product here to check if it's inside the plane, inside of those 6 planes. Use the AND operation to check if it's inside the view frustum. Don't worry too much about the implementation details here. You can afterwards take a look at it. And the sort function uses the typical quick sort implementation, which you can find online. It's a very well-known sorting algorithm. It's not necessarily always the fastest, but it works very well for this type of problem, as you will see later. And afterwards, the main new part is we have to create all the data structures. Evidently, for that we also need to allocate them. One thing is if you use jobs and the dot system, those data structures and arrays are not taken care of for you like that's usually the case with model behaviors in C#. You actually, when you have data structures like arrays, you actually need to allocate them, and in the destroy method you need to dispose of them. As we can see here, on destroy we dispose of all those arrays which we allocated with the persistence modifier, because we basically create those arrays, but we are then responsible also to dispose of them once the work is done with those arrays. It's not automatically taken care of, but that allows you to have basically no garbage collection and gives you a better performance overall by you doing it that way. So we have the hard data, the pool records, and then just the 6 planes which we need to do the calculations. And I walked through this implementation very quickly, and again, it should just give you the high-level picture of what we did, and the more important part is like the strategy or the tools you have in the dot stack rather than the actual implementation. Here we do exactly the same thing as before, and then we go through them, set the main camera, And then in the updates method, we add a little tool that we can toggle between using the worker threads and running it on the main thread to see what is the performance we actually gain by running something on the worker thread instead of on the main thread. And then we calculate all the planes. We set that those planes to be used based on for every update as the planes change when the user changes the camera. Then we create that job and we pass in the data points which the job needs to execute. If we use the worker threads, then we use the schedule method. Otherwise, we use the run. So when you call the schedule method, then the Unity will basically decide for you if that method should be run on the main thread or on the worker thread. It's not guaranteed to run on the worker thread. With the run method, it's guaranteed to run. It's basically a synchronous execution, so you can directly apply the records because you're guaranteed after the run has been called that the job is basically finished. If you schedule it and then you schedule the whole jobs, then you basically have to call complete before you can apply the next method on the finished job, and that's why we give the thread a little bit of time, and we only in late update, if the worker threads are used, we actually complete the job, and then we apply the records, which is just setting the actual position of the pooled hearts to the correct ones which we have in the pool records, and the pool records are just there that the 1,000 hearts which we actually need get clearly identified, and they also know if they have been visible or not in the last frame for a small optimization. Anyway, a lot of code, but the main important part is we have now the opportunity to execute work not just on the main thread, but actually on the worker thread, although with the caveat that we have to probably implement a few functions like the sorting and the frosting calling on our own. So let's go back to Unity and click play and see what the performance benefits are when we run something actually on a worker thread. So we can see here nothing changed yet because we're still running everything on the main thread. So we quickly type on J. So now we start to use worker threads and we can see that the performance is exactly the same or even slightly worse. Let's have a look at the profiler because something is weird. So we should see that the job is now executed on a worker thread instead of the main thread, if Unity decided to actually run it on the worker thread. And we can see here that the heartspool.update function is run on worker thread, and it takes up a lot of time. And the actual late update function has to wait for that job to be completed. So although we moved the work away from the main thread, because the late update needs to wait for it, we actually didn't gain anything. As you can see, like the performance is basically equal or worse. It's not executed on the main thread, but it takes either the same amount of time or even more because we actually have to do all the scheduling to be able to work on a different thread than the main thread. And so it looks like all the work we did to use the job system was actually not worth it. It just made things worse. We can see that here that the Hearts promo logic, although it's running on a worker thread and not on the main thread, it just takes basically the same amount of time and we didn't gain anything. The frames stayed exactly the same. So it looks like the job system is not really worth much if you have an operation which is taking up a lot of time and you need it to complete in the same frame, which is most of the time the case. But wait, there's one thing which the dot stack also offers. Apart from the jobs which you can run on worker threads and basically do asynchronous computation in a smart way, you also have burst. And burst is probably one of the most exciting technology pieces which are available for Unity developers now. Of course, it's relatively complicated. You need to add the burst compile attribute to a job that it is burst compiled. And if you wonder if that is really everything you need to do, it's actually true. Once you have a job function done in a proper way, like with burstable types, etc., as we did here, then the only code change you need to do that you can use burst is to add that attribute on top of the job. And burst is, let me first show you what burst actually can do. So here, let's try to rerun the whole simulation. It should have recompiled. And now let's see what happens when we run exactly the same implementation, but this time with burst. And look at this, we somehow are nearly running at 40 frames, from 30 to 40 frames a second. It's only become a lot smoother. So let's have a closer look at what actually happened when we look at the profiler. Strangely enough, like when we look here, the hearts pool job update, the method before, which run on the worker thread. Oh yeah, we have to actually run it on the worker thread. Let's continue the analysis and run it actually on the worker thread so we can easily see how much time it actually takes. So here we are way above the frame rate we had before, and let's have a quick look on that job being executed on one of the worker threads. So we're just adding burst compile to it. The job runs a lot faster than before. And actually, when we look at that from before, here we saw it run in 11 milliseconds. When we look at the profiler and we look for that worker thread, and we see that the hearts job, which before took up a lot more time, we can see that the time was vastly reduced compared to before. And we can see that basically here the job gets scheduled and then it completes in late update. And the time it took is vastly inferior to before. So when we actually look closer, the update function went from around 40 milliseconds to 4 minutes. So we have a roughly 10x improvement by just adding that small burst compile on top of the method. And that's just the fascinating part about burst. Burst basically understands the mathematics code and the other code you write to its intrinsic parts and optimizes it for the processor to be executed in the most optimal way possible. So it gives you a possibility to actually run code as fast as if you manually by hand optimized it in the C++ line. Like if you would try to get the best performance possible out of your code by aligning everything correctly in memory and doing the perfect alignment so that the least amount of machine instructions are used. That's basically what Burst does for you in general. And it's incredible how much performance boost you can actually get with that by just adding a little burst compile on top of a job. And that is what makes the whole thing incredibly powerful. That's one of the main things why the dot stack becomes so interesting. Yes, you are restricted in the data types you can use and how you have to write those jobs, but once you write them correctly, you can use burst and it just catapults the performance by a factor, by orders of magnitude. And depending on what you do, it can even be more than 10x. But of course, we're not finished yet. So we now go to the fourth iteration. When we go for the fourth iteration, we notice that we basically have one job now doing everything. And what if we would actually split up that one single job which does all the work into multiple? Because if we have multiple jobs doing their work, we can actually distribute them over multiple worker threads as long as they don't depend on each other. But if they do depend on each other, then we can use the dependency management, which basically handles all of that for us with having multiple things doing things concurrently. And we don't need to worry as much about read and write access to the data because Unity basically provides an easy way to actually handle all of that. So we decided to go with the pull records reset. That's the resetting we do in the beginning as a separate job. Then we do the culling, like testing if something should be visible or not and how close it is to the camera as a separate job. And the sorting as well is now a separate job. And then the swapping job where we exchange the ones which should be visible or not to be in the beginning, and then those real hearts get the correct positions of those hearts which are currently visible. Those are the 4 jobs we want to separate off everything to. And we also see here the job dependency is basically that the resetting of all the values from before, that doesn't need to happen in the beginning. It can actually happen during other jobs work. It just needs to be finished before we do the swapping, because on the swapping there we basically set if it should be writing this frame or not. Then we have the culling job, which needs to happen before the sorting job, as the culling information is important for the sorting job to know which hearts have higher priorities than the others. So let's quickly jump into the actual implementation. And here we have the 4th version of the code. And the main thing is that we have the same hard data, we have the same pool records as we saw before. The reset job is now separated, and that is a very simple job, and it uses the iJob4 implementation. That is basically a job which takes an index into account, so the execute method gets that index, and the iJob4 usually operate on arrays and get the index from that array element, and then we get out the record, the pull record, and we just set the write is frame to false, and then we apply back to the array that the data is actually written. As we all know, structs are actually passed by value, not by reference, and so we have to assign it back to the native array. And that is the only thing this job does. And the interesting part is here, you don't need to handle actually the array directly because you get the index of where to operate it on. And there's another few benefits you get if you implement the iJob4 interface. Then we have the hard culling job, which also implements the same one. Here we go just through the array of hearts and step through each one of them and test if they're visible or not and the distance from the camera. The main important part is, as iJob4s are possible to run on multiple threads, multiple worker threads, they actually can be executed in a concurrent way, which is extremely powerful, but it has one restriction. You cannot just write to all types of arrays which you pass in. You can only write to the array where you pass the index in, so Unity knows that you're currently operating on that array and nothing else basically writes to the same array while you execute that job. That's why the planes array, which we don't actually modify in that function, we need to indicate that it's a read-only array, so that way we can actually schedule the job not just on one thread, but actually multiple threads, which allows it to run in a lot more efficient way if we have a few worker threads available. So those are jobs. Then the sorting job is exactly the same thing as we had before. In the execute, we just do the sorting of everything, and that should basically lead to the exact same performance. Now just we can schedule it on after all the jobs have been run, or certain jobs could run in parallel if they don't depend, the sorting doesn't depend on the finishing them beforehand. And then we have the swapping job, which just does the same code as before, now just as a separate job. So that's all that is needed. And then here we just schedule all those jobs. So we have the reset job for the resetting one. We just scheduled that one, and we can pass in a dependency. And as we saw here in this one, this job will have no prior dependencies, but the hearts culling job also can start at any point in time. But the sorting job needs to depend on the culling job, and as well as the heart swapping job needs to depend on both the heart sorting job and the pool records job to be finished beforehand. And this we can see here, that this one has default means just it doesn't depend on anything beforehand. The same is true for the hearts culling job. That one doesn't depend on anything, but the sorting job here depends on the culling job, which we defined here. So this one gets passed in as a dependency. That means it will only run the sorting job once the culling job is finished. And in the end, we then need to have the two jobs combined. So the resetting job and the sorting job are then combined into a new dependency, and that one gets passed into the hard swapping job, because we saw before the swapping job needs to have both the culling and sorting job to be finished, as well as the resetting job to be finished. And by doing that, basically Unity can guarantee and analyze the code in that way that we know that this job will not run before the others two have finished. And then we just schedule all those jobs, and in the late update, to give them a little bit more time, we complete them, and then we apply the records as we did before. So let's have a quick look into Unity, what that actually helps with, if it actually improves or decreases performance, and what the main usage is of that. So as we can see, that separation of jobs sometimes helps when we are basically having the same camera position, but as soon as we move around or move the camera, it still is better than before. but it's not perfect. So let's maybe have a look what the main difference is when we go into the profiler to see what actually happens with those jobs. Are they scheduled in a way which we hope for, that they're on multiple worker threads and can distribute the work more evenly? So we have here the hearts sorting job, which takes up a lot of time, actually 9 milliseconds. And we have the hearts culling job, which also takes up nearly 1 millisecond. And because they both depend on each other, even if you run them on a worker thread, they don't benefit a lot from it because they're basically having to be run one after the other. And we see that the little swapping job, which happens after those two, is very short and doesn't need a lot of optimization. So when we look at those results, like, it already is better, but splitting up those jobs into separate ones doesn't bring as much because most of them in this specific scenario actually depend on each other. So we cannot parallelize the work in a good way. And evidently the culling job and the sorting job are the most expensive. So what if we are actually looking at our current problem and see what we can do to improve it? Let's start to be smart about the sorting. And also let's try to distribute actually the culling job, not just on one thread, because that one can easily be multi-threaded because each data is operated on individually. And if the culling job can get faster, basically our bottleneck gets a lot faster. So let's go into that. So we know that the hard sorting job takes up quite a bit of time, and also the culling job takes up not a quite significant portion of the performance. So let's go back into Unity and see what happens when we implement those improvements. So back in the editor, we can see that the sorting job, what can we do? We know that we need to have the 1000 best hearts to display, but actually the order of those 1000 hearts doesn't matter to us as much. I mean, if the first 1000 hearts are in the correct order based on the distance of the camera, or if they're completely jumbled up, we actually don't care. We also can know that the last few hearts, as long as the ones after the 1000 hearts which we care about, they can be in any order. So we actually can do an early out on this algorithm, on the quicksort algorithm, if we take those two conditions into account. If we know that the index we're currently looking at is actually like inside that pool of hearts which we care about, then we don't need to continue sorting it further down. That's a particularity on that quicksort algorithm. And the same is true if you are way beyond the part where we actually, of those 1000 hearts, if that one gets sorted correctly, we don't care about. So that's a way where we can do an early out. And the interesting part is here that thanks to Burst, you can implement a custom sorting function and run it at the same performance as you would when you would be an engine developer and had access to C++ bindings and do some kind of magic there, because Burst gives you raw metal performance, which is basically close to the absolute optimum you can get. So you can implement your custom functions and don't need to rely on other libraries which maybe had access to the underlying architecture of Unity that they could implement something faster. For example, the NavMesh agents definitely have an advantage from Unity because they run inside of the engine code, and so they can do optimizations which other NavMesh frames maybe couldn't have done. But now with the Burst compiler and the job system and all of that, you actually can get to the same performance as the Unity engine came to. So you're not anymore limited. You don't live anymore in two different worlds and only one part you can do, and you can only do so much. You can now get to the same level of performance as Unity did by doing their implementation, which opens up a huge amount of possibilities for third parties to give solutions to the Unity engine which run as fast or which are basically on par and have no restrictions compared to the Unity engine directly having that implemented, which is extremely exciting. And you already can see the little bit on the asset store of those developers which have taken up the job system and the Burst compiler to actually optimize a lot of their implementations, especially when they were very computational heavy. And the second part of the optimization, apart from being smart about the sorting job, is that we, instead of running it on one thread, we just run it on multiple threads. The culling job can easily be parallelized because we don't care about the previous or the next data point on that culling entities. It's just like one which needs to be looked at. And the only thing we need to change to actually be able to do that is you have to implement the iJob4 interface, and we have to do a schedule parallel. Then we have to give the length of the array, and just we define an inner loop batch count of 16. The number here is a little bit difficult to explain what is the optimal here. Often you use the profiler to figure out what is the best, but usually you go by a multiple of 2, so 2, 4, 8, or 16, 32, etc. And this job doesn't depend on anything. So by just doing those small changes, let's see if we see any performance improvements when we run the application again. So here we should now see, especially when we go into the profiler, that the culling job now is distributed over multiple frames, and the sorting should be a little bit better. So as we can see here, we are now averaging around 47 frames a second, sometimes even higher depending on how warmed up it is and how the recording is currently going on. Stay here. Yes, we can see it's actually running on a quite better frame rate. But let's have a look at the actual profiler and let's see if we can find out what is happening. So the first question, of course, we have is the culling job distributed over multiple frames? And we can actually see through the profiler indication that even though it's not equally distributed, it's definitely distributed over multiple frames. And we can see that each job itself takes 0.3 milliseconds, and the total is 2.52 milliseconds of those 16 instances. So that definitely helped to distribute the whole, even though the actual total time of those 16 instances is longer, the time it takes for them to finish is actually faster because it's distributed over multiple threads. So the actual time it took for that to finish is 0.3 milliseconds, and even though in total it took 2.5 milliseconds. And then we also have the hearts sorting job, and that got a vast improvement. Instead of n log n, we actually are more at the 2n of complexity with that algorithm, just because we figured out that we could early out because we don't care about the perfect sorting order of those hearts once they are inside the pool size or outside of the pool size. So it means with those small, simple, clever implementations, one using primarily the job system of Unity and the easy way to multi-thread something and distribute over multiple threads and the concurrency and all of the other stuff they implemented. And the other one is just being smart about the custom algorithm of figuring out how to improve on that. So we can see, so we early out, we distribute the calling job over multiple threads, and that actually led to us to get very close to 60 frames. We have performance sorting with the highest performance now is instead of 2.7 seconds, it went down to 3 milliseconds when I recorded that without the recording going on. And the calling job is now distributed over multiple frames, as you can see here. And here the total is nearly 2 milliseconds, but because we distributed them over multiple frame, the whole thing is actually taking up 0.1 milliseconds in total. So distributing the calling job over multiple frames had additional advantages. And that's why having burst and being smart with a burst, with the implementation of burst, actually can give you a huge amount of benefits. And we are very close to the 60 frames a second, which we definitely want to target with that hearts promotion logic. But it's not yet. Let's go and have a look at what else we can do. The fifth iteration. We saw that the model behavior update of the hearts is quite expensive. When we actually look at it, the heart promo logic update function itself, even though it takes up nearly no milliseconds individually, because we have 1,000 of them, it nearly goes to 1 milliseconds of time being taken up by that function. And as we already know how to use jobs, and we know that the update logic basically doesn't depend on other hearts, so it's very isolated, we can run that multi-threaded with an iJob4 interface. So we basically do the computation of how the heart should look like on the thread and distribute it over multiple to further speed up the performance. And let me go into the implementation for this. Again, for all the rest, all the other improvements we did in the past, of course, we keep. The only thing we improve upon now is to have that hearts logic, instead of being done on each heart individually, the hearts manager actually takes care of all of the hearts and does it for all of them. And we basically need a new structure, which is called the hearts promo logic transform value, which has a position and a rotation. And with that, we have a new job, which we can find here. These are all the same jobs as before, the swapping, the sorting, the calling. And then we have the hearts promo logic job. This is again an iJob4, which basically goes through an array of data points and then extracts it. And here we just do exactly the same as we had in the hearts promo logic update function. It's basically just this taken into here and doing exactly the same. Now, that is basically the only thing we do in addition to all the other optimizations we did in the past. And let's have a look of what that actually benefits us with, or if it actually stays exactly the same as before. So what did we discover in the results? We are still more or less at the same performance. We just moved that 1 milliseconds now for the hearts promo logic job from those roughly 1 milliseconds from before. We actually managed to reduce it to 0.33 milliseconds. But writing to the actual transforms is still quite expensive. But at least we already reduced those transform logics from doing it in the update by doing it in a job by a factor of 3, which is already quite good. Now let's push it even one step further. The bottleneck is now actually primarily the updating of those transforms with that logic. And Unity actually has implemented a new way of modifying transform values with a so-called transform access array. And when we go to the last version, which we take a look at today, the last iteration, we can see in version 6, we have one new implementation. Of course, all of those are burst compiled. We have a method called iJob4 transform. And that allows us to actually have a transform access array, which allows us to modify directly the value of model behavior transforms inside the job when it's burst compiled, which means we can speed it up heavily. So we have here exactly the same code as we had before, the oscillation, but now we can directly modify the local position and rotation of a transform with the transform access array. And to actually do that, we have to do nearly nothing. We just have to create a transform access array here, which we call child transforms. And then we can go here, we just add the actual transform, which is the child transform from those hearts, the part which actually rotates, which before had the heart promo logic on it. We still leave it there, but we disable it so it doesn't do the computation twice. We add that hearts promo logic transform to the child transforms. And then when we have that in the update method, we can just simply schedule them. After the whole logic has been done and we have identified which hearts actually need to be updated, we can here then run this heart promo logics job where we pass in the child transforms of those heart transforms. And this job doesn't depend on anything because we know all the jobs have been completed beforehand. And we actually can see afterwards in the profiler how well this actually worked. And we first let it quickly compile that we can see what is in the last iteration, what is actually the performance of the game after we added the 100,000 hearts to it and how well it actually works. So we can see here we are, even with the profiler running, we are very close to the 60 frames. Sometimes it goes down, and especially because I do a screen recording now, we are here at an average of around 45 frames. Without the recording, we easily manage to get around 60 frames a second, even though we run the hearts job, the calling job, the sorting job of those number of hearts in the game, and we can see the hearts are clearly visible everywhere. And of course, we could push it a lot higher if we wanted to, if we had a lower target of maybe only 30 frames. But for the moment, we leave it at that. And we actually can see that we are averaging around 55 to, definitely above 30 frames a second. We managed to, through that transform access, we actually managed to reduce that heart logic even further to 0.06 milliseconds from the 0.3 milliseconds. I mean, it's already very little time which it takes, but any further improvement is still incredible. And through the transform access area, we actually managed to reduce that by a multitude. Not exactly a 10x reduction in time, but very close to that. So now to the conclusion. I know there was a lot of information. I don't expect any of you to be able, if you have never heard of dots or the job system or any of that, to implement all of those methods right after hearing this talk. That was not the goal. The goal is that you can see that even if you use mono behaviors now and you only want to use the production-ready parts of the dots technology stack, you can still use it in your current game to actually achieve incredible performance. So it also, with the transform access array, we saw that Unity has a tight integration between the job system and the transform access arrays, that you can actually use it for mono behaviors as well and not just in the ECS land. The hard logic, which was evidently very simply implemented in the beginning, where we just spawned a lot of hearts in the whole volume, was completely impossible to run. I mean, we went from basically 3 frames a second to up to close to 55 frames a second. So it's evident that the dot stack can give you incredible performance while you can do engine-level performance implementations of sorting and custom functions, and you can actually use the burst compiler to do something which was completely impossible before. I hope that small little overview helped you to get at least excited and maybe learn more about the dot stack, and we hope you have a few questions, and we cannot wait to answer them. Thank you. Okay, I hope that was, at least to some point, understandable for many of you. It's definitely difficult to wrap your head around what are political types, like how to implement the job functions, etc. And also there were some algorithms which are not easy to grasp if you've never heard of Quicksort and you don't know how to get an early out. But we will make the repository available for you to investigate later on after this webinar. We will share it afterwards with the links. It will be on GitHub, and you can then browse through the code. And when you join our the Xrbook and Discord, you can also ask questions there if certain things are still not clear. But we have an additional section prepared. Brian will talk about the ECS part, which is actually highly exciting, especially because job dependencies become a little bit complicated if you start to modify things and need to think about it. And ECS makes a lot of things a lot simpler, especially pooling of game objects is not anymore needed, as you can spawn thousands of them in one frame and it doesn't cost much. So it's a highly exciting technology stack, especially also Unity Physics, which is a stateless physics engine. There's so many cool things coming down the pipeline, but I don't want to take anything away. So Brian, please go ahead with the ECS part.
Okay, thanks very much. Let's see. So it looks like, I mean, in terms of official clock time, we have like 5 minutes, but I think we can go beyond, and it's not an issue, right? And we can do the Q&A after I speak for maybe 10 minutes or so.
Definitely.
Sure. Okay, cool. I do want to note though about Roger's example project. I should note, like, you should understand, like, the only way to truly accurately measure performance is to not do it in the editor and not while you're recording either. That is going to mess with your results. So you saw like some inconsistencies in some of what he showed there. So that's an important point. Also, I will note, actually, I believe, I wonder if you looked at collections, Roger, there should be a sort provided for you in the form of a job that is already, you probably didn't have to implement your own sort, I would guess. I wonder if you looked at that. And also one more comment on that is that just looking at my first guess is you probably could solve that problem most effectively by spatially partitioning the hearts. Like, break your world up into a bunch of grid cells. I'm sure you consider this, but for educational purposes, I understand why you did what you did. But like the way you probably solve that particular problem in reality is you want to like break things up into a bunch of separate lists bucketed by grid cell, and then you wouldn't need that. That probably would solve most of the performance problem in that particular case. But otherwise, it's nice to see that like progression of here's a single threaded job, now parallel and bursted. That was cool. I will also, last thing you just said is you said entities allows you to create a bunch of game objects and not worry about pooling. That's not accurate. Instead of game objects, you create entities, and those you don't really typically have to worry about pooling. In fact, I can't think of a case where you would, honestly. Okay, so now I'll get into talking about entities. Sorry for correcting you so much. The performance problems we're trying to solve with the entities package is that you want, as much as possible, your data access to be cache friendly to the CPU, and you want the code itself to be cache friendly. What does this mean? So, sorry, I'll try to slow down a bit. So, in a modern processor, in a modern system, the CPU tends to be way faster than the system RAM. Right? It's orders of magnitude faster. And so anytime the CPU has to actually read and write memory, it's going to sit and stall. It's going to wait. So that's why we have a cache sitting in between. And so anytime you access an address of memory, instead what happens is it gets pulled, it gets copied from main system RAM into cache, and then CPU then reads it from the cache. And the next time the CPU then has to read that same address, if it's still sitting in the cache, then great, the CPU doesn't have to wait for the CPU. So these units of memory called cache lines, which are 64 bytes on most platforms now, when you access a single byte, you're actually grabbing that whole cache line and it's getting copied into cache. So you access that byte again, or any of those other 64 bytes, it's probably still sitting in the cache the next time. So ideally, when you access data, as much as possible, you want the CPU, all the data it needs, to already be sitting in the cache. Now, obviously that's not always possible, but the question is, how can we try and bias things, arrange things so that's usually the case, at least for our most important workloads. And very, very hopefully there's a feature of what memory systems will do where called prefetching, where if you access a certain byte of memory and the CPU then goes to the next byte, the next byte, the next byte, if you start reading through memory sequentially, the prefetching logic of the memory system will kick in and say, aha, I'm going to guess that you probably need the next cache line after this one. So I'm not just going to I'm going to go ahead and grab that while you're still working with this cache line, and probably by the time you get there, it'll probably be sitting in cache already for you. So it's very much like laying the train tracks right down before the train gets there. That's what you want with prefetching. And so then if you go process some big array, if you go loop through some array of bytes, what you'll get a cache miss probably for that first byte. It's probably, if it's not sitting in cache, the CPU will stall waiting to bring that into that cache line into memory. But then all the other cache lines of that array, thanks to prefetching, the CPU usually doesn't have to wait in most cases. So as much as possible, we want to try and arrange our key data, the things that we need to process at scale. We want to put them in some big, nice contiguous arrays. That is what we're trying to aim for. And then the story with code caching is that, well, let me go back again so that doesn't distract me. Oops. Too much. The issue with code is that code itself has to be loaded from memory into cache before the CPU can execute those instructions. And so ideally, when code executes, all of the instructions are already sitting in cache most of the time. So an anti-pattern, what you don't want to have happen is, say you have 1,000 monster objects, and they all have an update that needs to be run. And what you would want is for, in a single frame, that update method for that monster to be loaded once for that frame, and then you loop through all the monster data and run the update on each one of those monsters. That is a sensible, obvious thing to do. But if you update one monster and then go do something else, run some other code, and then update another monster, go off to something else, and then update the next monster, if you like interleave the updates of your monsters with other stuff, well, that other code itself has to be copied from memory into cache, and it might overwrite the monster update code into cache. It'll temporarily overwrite it. So the next time you update a monster in the same frame, it has to load it again. So like in the worst case scenario, if you update 1,000 monsters, you might end up reloading that one monster update method code 1,000 times, which is obviously very stupid. We don't want to do that, right? And you might think, well, surely Unity with mod behaviors doesn't do that. If I have a bunch of 1,000 monsters of all the same type, it can surely like group them together, their updates, you would think. For good reasons, it doesn't actually do that. So you do get the bad case, the anti-pattern in the context of mod behaviors. So that is one thing that entities needs to fix. So the entities package itself. So the performance problem we're trying to solve is cache-friendly data and code. And what entities is an implementation of an architectural pattern that is known as ECS, standing for entities, components, and systems. Be very clear, it is not a system of entity components, it's a thing with entities, components, and systems. That's the proper way to read it, really. So the entities and the components are the data sides of things. And I don't have the time to go into details in this talk of precisely how things are laid out, but the gist of it is we want that component data in those entities to be laid out in nice big arrays. So for most of our purposes, most of the critical parts of our code, we can just loop through them in nice big linear fashion and get the benefits of prefetching for the most part, and avoid a lot of CPU stalls, avoid a lot of the CPU having to sit and wait for data access in many cases. And then on the code side, that's the systems. Systems are, kind of skip ahead. Systems are extremely simple, really. They're just a thing that has, it's a type you define with an update method, basically. And that update method will run once in the frame, just once always. And kind of handily also compared to mono behavior updates, these system updates, when you care, you can actually specify, oh yeah, I want this system to run before this other one in the frame. So that's kind of handy. You can't really do that with mono behavior updates. You can put things in pre-update and late update versus update, but it's not as flexible. You don't have as much control there. So that's really all there's to say about systems, really. So going back to the entities. Entities are basically analogous to game objects, pretty much. They serve pretty much the same purpose. But in terms of data, they're very different. A game object is an actual managed object that is a container that contains a number of components. It has like a list of components that it has. Whereas an entity is just an ID number. It's just this tiny little int, basically. Or int, yeah, excuse me. So the components, meanwhile, are themselves unmanaged objects in most cases. They're struct values. And they, again, I can't go into details here, but they end up arrayed in nice big arrays. So if you have a bunch of foo components and bar components, your foos will, for the most part, be in a bunch of nice big arrays, and all your bar components will be in a different set of arrays. And so when it comes time to access, hey, I want to loop over all the entities which have a foo and a bar component. I want to process each one individually. I want to visit each foo and bar of each entity one by one. You can do that with nice big linear array access. That is the gist of what we're shooting for. That's what everything is optimized for in entities, is that particular case. Now, to be clear, in some kinds of code, you just naturally do have to skip around memory. You have to jump around and visit this entity, which links to this other entity. That some use cases, that's just necessary. But the idea is we're optimizing for like the important cases, the big cases where we need scale. And that's in those cases, you can usually go through these components in nice sequential order. And very importantly, you can access these entities and the component data in jobs. So it's all in managed data for the most part. And so that can be used in jobs. And so you can, jobify that code that processes your components and burst compile it. So you get all the benefits of all the things that Roger was just talking about right now. So I do strongly encourage you, if you are interested in looking at entities right now, I strongly encourage you to, maybe I'll go find some links that I can post later, but there are already a lot of talks to talk about more detail about precisely how the data is laid out in these things called chunks. It's not really complicated. Oh, sorry, this is my cat. It's not really complicated, but it really helps to understand that data structure. 1 second. So I'm going to have to eject my cat from the room in a minute. So the question then is, okay, you're going to make your game out of entities instead of game objects, perhaps, or possibly have them live side by side, but you want to be able to construct a scene of game objects, a scene of entities, right, and have them loaded as a scene. You would think then that in the editor, you would have a kind of scene where you can just directly say the scene has this entity, that entity. But actually, for a number of reasons that are kind of complicated, we instead have you create a scene out of ordinary game objects and give it components. I'll move in a second. And the idea is that at build time, we want to convert that list of game objects and their components into a set of entities that can then be serialized into a file, and then that is what is loaded when the scene runs. I'll be right back. Sorry.
Maybe we take one of the questions. Brian has handled his little kitty. So we have one question was, if you have studied computer science and you have maybe lived a few years inside Unity, if you basically need to unlearn everything you know and start again from scratch because dots and data-oriented programming is so much different from what you're used to. Maybe Brian, as you're back, can you maybe help answer that one if you think it's useless now and everything is new and fresh?
Well, when we do our internal dots training, we train up our own people on using dots. Part of it is emphasizing data-oriented design principles, which dots is sort of structured around, hence the name. In some sense, yeah, you are relearning habits, but I can say, particularly with the non-entities parts of dots, jobs and bursts mainly, I would recommend you can find selective use cases for them. Where you have to get familiar with the API, but that's probably the best entry point to dots. Because when you do use entities, you're going to want to be using that stuff as well. So I think that's probably a good entry point at this point for getting bursts and dots, is trying to find some opportunity of, I have this one particular hard computation problem in the context of my normal Unity game. Let's maybe try and experiment with using jobs and bursts for that part. And then maybe we should come back to this. I bet Fabrice has some thoughts. So
yeah, I think overall, if you ever, I think your experience in computer science probably will help you understand how amazing the job system is. Because if you ever have to implement something by hand with logs and semaphores and all of that, and know how hard it is to get that right and actually working properly in all circumstances, I think your computer science background will probably help you appreciate how much easier it is with all the tools offered by Unity. But I don't think it's useless that you have learned about databases. ECS is very similar to a database. So I think you can benefit a lot from your previous experience. It's just you might need to unlearn certain things or be a little bit questioning more what you did in the past and maybe be open for new ideas.
Yeah, with entities in particular, if you're going to make a game that's all in entities, that is a head spin in many ways, and it takes some adjustment. Once you get used to it, I think in many ways it pays off and is simpler in the end. Like a lot of bad patterns. I have a video on YouTube called Object-Oriented Programming is Bad, where I make an argument about how object programming leads you astray in all sorts of ways, and it's very easy to create messes. Right? I have found in particular, once you get past the entry point, the learning curve, you end up creating code that's a lot simpler ultimately and easier to reason about, not just for performance's sake.
fast and